Good morning, everyone. We're just about to start our teleprotection talk this morning, so just waiting for a few more attendees to join, and then we will get into it. So I'll just give everybody a few more minutes before we kick off. Okay, for those that have just joined us, thanks for joining our teleprotection session this morning. Just waiting for a few more to join, so just going to hold out for 1 or 2 minutes, and then we'll get into it. Okay, great. I think we've got most folks online, so thanks everybody. Today I'm just going to start by introducing myself and James Dowell, who is our R&D manager. So my name is Paul Reid. I'm the CEO of Mimomax Wireless, and today we're going to talk about teleprotection technologies. My background is not in control engineering, it's in radio engineering and RF engineering. So that's where our expertise is in the communications networks inside of teleprotection. So we're going to talk a bit about that today and how that relates to Mimomax products as well. James, if you wouldn't mind introducing yourself.
Yeah. Hello, everyone. I'm James Dowell. I'm the development manager at Mimomax. Like Paul, my expertise is around the communications side of things. My background is in signal processing.
Great, thanks, James. So just going to fire up the presentation and just do a quick check that James, you can see that presentation okay?
Yes, Paul.
Yeah, great, thank you. So this morning we're going to talk about solving some of the critical communications challenges for teleprotection. And we've done the introduction, so we're not going to waste too much time on that. And most of you will know Mimomax. If not, then you probably find us on our website and find out a little bit more about the history and background of the company. But our focus is really on solving critical communications challenges, mission critical challenges, and working on a number of communications fields, such as field area networking for utilities, land mobile radio backhaul, and teleprotection. This is the third, and this is a series of webinars that we've done, and it has been probably the most subscribed webinar that we have done, just around, and I guess the interest being piqued around teleprotection is prevalent at the moment globally, is what we're seeing. So just in terms of teleprotection 101, relays sort of two main functions, really isolating faulted sections of the system and maintaining power delivery capability in the rest of the system. So looking at where the potential for human life to be endangered, damaging system and equipment, we want to minimize that, and also reducing instability in the system as well. So ensuring that we act quickly to protect circuits, equipment, and people. And often there's a latency requirement around that is quite quick. So within milliseconds, we want to be able to trip these relays and protect human, equipment, and stability of the system. So here is an image of what a typical transfer trip type relay system might look like. And what we're seeing here is a relay at both ends of a transmission line. And the idea here is that we're protecting the transmission infrastructure and ensuring that we are using communications devices to monitor both ends of the network and apply those relay signals and switch those relays really quickly. So some of those may be performed across fiber interfaces, analog interfaces, G703, or synchronous serial RS530 or X21. So the systems that we're talking about are agnostic largely in terms of the interfaces and protocols that we'd be using to communicate. But these have to usually be enabled within milliseconds. So often there are requirements around how quickly we want to be able to switch these relays, and that is often fractions of a cycle. And if we're talking 60 hertz, and that's around 16 milliseconds. And while standards would say often you can operate within 3 to 5 cycles, the sooner we can get those relays tripped, the better, and that is often dependent on the communications link, amongst other things that might sit in the chain. So the most common schemes that are used for teleprotection are the current differential schemes. That's where we're looking at the local relay receiving the data from the remote relay, and it's used to develop magnitude and phase angle, which currents that are measured by the remote. This is compared with the local end, and the signals are sampled and at each end of the line and synchronized prior to comparison to avoid introducing errors. So making sure that time synchronization and symmetry in both ends of the communication system are aligned so that we minimize any false trips. Other schemes will include pilot wire, phase comparison schemes, and directional comparison schemes. So there's a number of different types of schemes which have different types of use and category within the system. If valid time sources are connected to relays, channel latency can be measured in both the receiving and transmitting directions. So looking to make sure that we are minimizing latency in both directions and synchronizing that latency and minimizing asymmetry across the channel. So the difference between the delays in the two directions is called channel asymmetry, and that has to be quite accurate, otherwise we can introduce faulty operation or false triggering of the protection circuits. So here's just an image of where those asymmetries can sometimes sit, and often it is across the communications network that we're trying to utilize to compare and then trigger the relay. So it is important that we minimize asymmetry in both directions. So tripping schemes, there are a number that people in the industry will know much more about than I do, but to just highlight a few of them: direct transfer trip, and they are related to breakers that are tripped upon reception of the trip command. Underreaching transfer trip, an underreaching element sends the direct transfer trip, and the underreaching refers to where that element sits in the electrical grid. So is it at the remote end or at the source end or the base end? So we were saying underreaching, it is not at the far end, it is at the base end or the source end, and overreaching refers to where we're starting to sample at the far end or the remote end. So it kind of depends on where in the network we are looking to source the data and actuate the relay. And also we have comparison blocking and directional comparison unblocking. So this is where the trip is used for an operation of an overarching element without reception of the block, and this directional comparison unblocking is where the block is keyed during normal operation, and the unblock is keyed when the overarching element operates. So different numbers of schemes or different types of schemes that are used in different applications, and all kind of wrap into the teleprotection requirements depending on where you are operating in the network. So jitter is the other important aspect. So asymmetry and jitter is related to measuring the delay. However, this time it is about determining the difference in the delay between the received bits. So when we look at the imagery that we're presenting here, at one end of the link we are sending our data, and at this point in time we're receiving that data within 2.2 milliseconds. So our signal has been sent within 2.2 milliseconds. However, at another instant in time, we are receiving that signal within two milliseconds, and the delta there is really 2 microseconds. So if I just go back and look at that and see the 2.2, then as we send the second trigger, then if that was at 2 milliseconds, then the delta would be 2 microseconds. So that relates to the jitter, and you can look at peak jitter or average jitter, but jitter is essentially the delay that varies over time when sending those signals. Teleprotection requirements. So general teleprotection requirements in terms of the communications network relates to the availability of the path. So ensuring that you've got a well-engineered path, and that would typically want to be achieving 5 nines of availability. The selection of appropriate communications devices, so ensuring that your devices meet the jitter requirement, meet the latency requirement, the full duplex aspect of what we're doing meets the asymmetry requirement. So ensuring that all of those requirements have been met, ensuring that you're not likely to get significant interference or transmitted over, that you have a clear channel, and all of those aspects get built into the design of the link. Ensuring that you've got compatibility between the devices, so whether it be a mirrored bits type of interface, an RS232 interface, E&M 4-wire interface, C3794, so ensuring that you've got compatibility between the interfaces and the timing and protocols that are associated with the system. System security, which means that the operation should not operate unnecessarily. So ensuring that the probability of getting a false trigger through some form of interference or other impacting signal is minimized, and dependability makes sure that it must operate when it's required. So ensuring that the operation is dependable and highly reliable. And these metrics come from a number of standards that have been produced, but one of the key standards is 6834-1, that's an IEC standard, and that is related to teleprotection equipment for power systems. So haven't got it listed there, but just to remind you of that standard, that is IEC 60834, and that relates to teleprotection equipment for power systems. So both latency, system security, dependability become a big part of designing that network. In terms of latency requirements, teleprotection really imposes the most stringent QoS on a communication system. Must be fast, secure, and reliable, and latency rates must fall between 5 to 10 milliseconds, and that relates to the energy equation and reducing the amount of energy in a fault cycle, and also reacting ideally within one cycle. So we look at these communications links and we see that they're governed by 3 categories. So the latency is one of the key aspects of those categories, where we see category 1 sitting below 6 milliseconds, category 2 at 10 milliseconds, and category 3 at 30 milliseconds. And obviously 6 milliseconds being the most challenging for category 1. So typical utility requirements, what we're seeing is latency that's less than 5 milliseconds for the communications link, asymmetry that's less than 2 milliseconds, and availability that is up in the order of 3.5 nines, but typically 4 nines in terms of availability for teleprotection networks is typical. We talked about dependability, and it is really based on ensuring that we have those comprehensive factors built into path planning, and that is 5 nines reliability and availability across that link, we have stable latency, and we have very low jitter. And I think that within the Mimomax system, we really talk about nanoseconds of jitter. What we've also seen across these teleprotection links for our utility customers is not just a requirement to run the teleprotection component, but also other applications over the link, which may be low bandwidth SCADA, it may be connecting to simple RTUs or other devices at the substation, substation SCADA, or also VoIP, so providing a voice channel into that remote substation can also be run across the link. And also we see the requirement around redundancy for the primary communications channel. So the systems that we provide often provide the communication link, which is primary, but often if there is a microwave link or a fiber link that's already in play, then our link becomes the redundant link and secondary to that. So it just depends on how the system has been designed. So there are a number of common methods in terms of ensuring that you maintain the minimum amount of time or the lowest amount of latency within the network. So what Mimomax use here is the use of time division activities such that we are allowing a time slot to be transmitted, and we dedicated a portion of that time to teleprotection traffic. So each time slot, and we'll show an image of this shortly, is dedicated to teleprotection traffic, and that cannot be impacted by any other means of traffic, whether it be other serial or IP devices. So we use the time slot method or time division, and that is always guaranteed to pass teleprotection traffic. Dedicating the other option is frequency division, so dedicating a portion of your spectrum, i.e. a narrower channel to teleprotection is another approach. And then there is IP packet quality of service marking, so marking for priority packets to ensure teleprotection takes precedence. So Mimomax don't use this. We don't often find that some of those QoS rules or how that's been set up will provide the most reliable outcome. So we have landed on time division, and I'll talk to that in a little bit more detail in the coming slide. So managing serial versus IP. So I mentioned earlier that we want to be able to do a number of things across the link. So we want to be able to perform serial communications, but we may also want to be able to perform some substation SCADA. We may also want to do some VoIP to provide a communications link at the remote end of the site. We also may want to connect to simple RTUs or other pieces of equipment or apparatus at the endpoint. So in our protocols and our teleprotection variant of product, which is a product that is optimized for teleprotection, we have got time slots. So these are blocks of time that have been segregated into 28-byte chunks, and we have partitioned those slots again into 2 blocks, one being reserved for serial data and one being reserved for other IP type requirements. So our teleprotection always runs by the serial interface. It is a high-speed serial interface which has media converters that come out and connect to C3794 or G703 or X21 interfaces, and our packets are 28 bytes, which I've mentioned. And what we're essentially saying is the teleprotection section of the block is reserved for teleprotection, and IP data is never ever allowed to interact or interfere with that serial piece. So across the teleprotection links, besides the relay switching and sensing and transfer trip type information that's being sent across the channel in the serial data, we can also provide that, as I mentioned, RTU, VoIP, or SCADA as well, given we have the capacity to be able to support those applications. So how does the time division work? So if we look at the serial input and we start to map that serial message across time until we get the output, and we've measured time here as 5.5 milliseconds, which might be typical of a 16 QAM modulation that's operating in a 25 kilohertz channel, for example. So when we just map that across time, you can see that the first time slot is, or 28 bytes is sent, and then the second one comes in, and we just continue to load up that data in those time slots. And the latency is really measured by the time it takes us to get that first packet across, that 5.5 milliseconds across that 16 QAM channel and that 25 kilohertz bandwidth. So it's just an example of what's happening there with the transmit and receiver and how those slots work. So narrowband communications versus fiber or microwave. Narrowband is often not considered, but more and more of our customers are turning to this for a number of reasons, especially given since it's been out in that market for a while. It's been proven technology. It works really well, and a lot of it really just comes down to ensuring that the link design is solid and investing in that 5 nines type of reliability. So fiber versus narrowband, obviously a high cost of install is really the major consideration for fiber. Sometimes the lack of inherent redundancy. So here is an image of a fiber link, and this happened in the earthquakes that Mimomax are quite familiar with here in Christchurch in New Zealand, where we suffered a 6.4 that was predated by a 7.1. I think in the 6.4, the ground movement was such that snapped that fiber, and it impacted a number of services from our local utility here. Thankfully, they had a good old narrowband wireless network in play, and they were able to maintain comms and get that network up and running really quickly in light of some fairly severe outages due to links, etc., breaking due to the earthquake. So that was a good lesson for everybody here locally, just around the value of narrowband. And even with ground movement, narrowband communications is not so reliant on pinpoint accuracy microwave linking. So what we see here is with the broader beam width, you can suffer weather events, you can suffer ground movement and tower tilts and twists, etc., more readily, just simply because the beam width is wider, and you've got much more tolerance around how you maintain the communication channel. That adds to reliability in the network. Microwave is really something that we're seeing a little bit more sort of hesitant challenges, I guess, due to the cost and the nature of the tower work, the size of the antennas, and really, I guess the total cost of installation has been the key thing for microwave, and that requires a really good path generally. So it's got to be line of sight, and as we said, you've got to have that pinpoint accuracy on those, aligning those antennas. Antenna beam width is narrow. Weather-related fading can be an issue, whether that be rain fade or other types of weather activity. And as I mentioned, the ability to cope with path obstructions, which sit in that microwave space that doesn't necessarily sit in the 1 gigahertz, sub 1 gigahertz narrowband space. So it means that we can have more tolerance and a little bit more resilience in different disaster events that may occur. The Mimomax optimized protection variant. So I just want to talk about the Mimomax technology, and we have technology that is, I guess, developed and optimized depending on the application. So whether it be a field area network that we're working on, which is a large point to multi-point network, whether it be a land mobile radio backhaul application, which does have a latency requirement but not as aggressive as what the teleprotection requirement is, whether it be redundant linking, whether it be a leased line replacement, or simply a SCADA point-to-point, point-to-multi-point network. Our products are optimized for those applications. So where we have taken some of the technology advancements from LTE, 4G and 5G, such as very high order QAM 256, we've taken MIMO obviously from those technologies. In this case, we've got built-in full duplex, but we've married that to the narrowband land mobile radio spectrum, and that is in VHF, UHF, 700 meg upper A block, 800 meg, and 900 meg in the United States. So what we're trying to do here is bring best in breed technology, but we have optimized it for mission critical applications and tailored that towards bands which are readily licensable, and essentially licensed spectrum gives you the most resilience in a world that is going more and more towards the wireless side and creating higher noise floors in environments. And you know, so it's licensed spectrum is really the most reliable of the options in terms of spectrum availability. Unlicensed is sometimes I hear unlicensed as being an option, but often what we see is challenges around noise floor and folks being transmitted over, and we're seeing rules that are changing in that environment in the US that makes that aspect of linking more and more challenging and dubious. So this is just a little bit of background into the technology. The Tornado radio is the radio that we are looking at here today with respect to the optimized protection variant. So we have an OPV, which is optimized protection, and that is optimized for these low latency type applications. So the enabling performance of the technology is MIMO. MIMO provides very low buffering requirements. So you couple that with full duplex, there's no half duplex buffering or delay while you're switching between TX and RX. So the MIMO speed is quick enough that you're minimizing buffering on the platform. You've got the full duplex, you've got the high order modulation, and that what that relates to is one of the world's fastest narrowband radios in the market today. It is spectral efficiency is 16 bits per second per hertz, which means for every 1 hertz of bandwidth, you can pass 16 bits of data. And that is typically at least twice what CISO would be able to achieve. And because we've built in full duplex and high order modulation, then you get the benefit from having those attributes built into the product as well. So far exceeds what a CISO radio or single antenna system can do. And also the duplex nature means that you are improving round trip latencies, etc., simply because you are able to transmit in both directions independently of each other, and those links will moderate themselves. So the downlink could be operating 16 QAM, while the uplink would be operating QAM 64. So that is independent and is dependent on what noise or interference you're seeing at either end of that link. So the system is smart enough to figure out what is happening at either end. When we're talking about land mobile radios, our customers are often surprised how many P25 or DMR channels that we can pass across the link. Oops, and let me just hit that. And that is something that we also offer in terms of land mobile radio backhaul. Ultra low latency, so typically sub 5 milliseconds in 50 kilohertz channels, and I think our specs are actually more aligned with 3 milliseconds, depending on the type of interface that you're using. The radio is Linux-based. It does support AES 256 and the security features that you would typically attribute to a utility-grade radio. The radio has been extensively penetration tested, and attributes like sticky MAC, where known MAC addresses are only enabled to interface with the product, port disabling. We've talked about encryption, stateful firewall. All of those aspects are built into the product, and the Linux platform provides us the ability to provide up-to-date IP networking type functionality and application within the platform itself. Flexibility, 12.5, 25 or 50 kilohertz channels, so they're software configurable, and is space saving. So 1 RU, the duplexes are built in to this product, so it is 1 RU and certainly much slimmer. I think it's about 210 millimeters, so it's slimmer than a 19-inch rack, so that can be wall mounted or rack mounted, or even it is ruggedized so that it could be outdoor mounted on a pole, and there is a hood that we place across the interface. With our 1+1 protected variant, that sits in a 2U 19-inch rack space, and if we're moving to customers are wanting to move to VHF, then we have an external duplexer. That just means that the duplexer gets large enough that it can't sit within the radio. It comes out, and that becomes external. Within the product here, what you see there in that image contains everything. It contains both transmitters, 2 transmitters, 2 receivers, and all the duplexing is built into the product in the 400, 700, 800, 900 meg bands. We have standards-based IP, SNMP v2 or v3. For the IP side, we support QoS with low jitter, 50 nanoseconds, and our bit error rates are typically 1 × 10 to the minus 6 or 7. I'm not sure why we've got 1 × 10 to the minus 10. That would be probably a very good working length there. It's configurable, so command line plus web interface network. So we have the command line interface as well as GUI, and they mimic each other, so they have functionality that is, and the ability to control the radio in a similar fashion, just by a different mechanism. Simultaneous serial and Ethernet, which we've mentioned through how we manage our teleprotection protocol, and supporting DMP3. And on the front of the radio, we have some digital I/O and analog input as well. So you can use the radio as an I/O device. Some of our users operate it as a small RTU. So it supports DMP3, so it's DMP3 addressable I/O. So we are using that sometimes to control and monitor doors, and because it's got an analog input and ADCs at the input to that I/O, you can also manage and monitor analog signals such as battery voltages or temperature as well, which some of our customers do. Voltage friendly, so 10.5 volts or 10 volts to 60 volts DC. Standby power of 5 watts and an average transmit power of 20 watts. And the range of communications can be over links as long as 60 miles. And so it provides very long range. And we can also perform multiple hops. And because we are full duplex, we're not degrading data. However, we double latency when we go to multiple hops. So the optimized protection variant of the Tornado is the OPVT. It is typically offering latency of 5 milliseconds, but can achieve rates as low as 3 milliseconds, and jitter minimized to 55 nanoseconds, which is well below the 1 millisecond recommendation. We talked about guaranteed priority by inserting the serial at the lowest level in the protocol stack and reserving that bandwidth. So never allowing the Mimomax or the IP side to encroach on the teleprotection piece. We've mentioned residual bandwidth, so allowing additional bandwidth for other residual use, such as IP SCADA traffic, and that has no impact on the dedicated protection circuit. So allowing IP SCADA, we mentioned the R2U, we mentioned the VoIP, without impacting the availability or resilience of the serial protocols that are running across the radio as well. Excellent coverage, high performance for both line of sight and non-line of sight. So one of the advantages of this type of technology when considering teleprotection is the need not to have to erect a tower, not to have a 6-foot dish requirement, but in many cases our customers can mount these on the top of buildings or with simple pole mounts and with much simpler antenna configuration. So it may be a radomed Yagi or a panel antenna, and as we said, they're much more forgiving in terms of bandwidth requirements. So that talks to a lower total cost of ownership. Our 1+1 system is a hot standby or /warm standby system. It relates to sort of minimizing data loss. So a no data loss operation system. It has multiple configurations to switch over. So it can switch over on serial data, it can switch over on GPIO, it can switch over on alarms, or it switches over on antenna port disturbance. So the applications around very mission critical primary communications links is where we would look to provision the 1+1 system, and or backup redundant links for use when the primary communications are down. So given it's a lower total cost of ownership, it also provides a lower cost for redundant linking. Our interfaces, so I mentioned earlier that we have the high-speed serial interface. Into that high-speed serial interface, into the radio, we have the option to connect a number of different devices and other interfaces. So what we're showing here is the synchronous serial interfaces for power line protection, and that would typically utilize C3794 fiber, X21, G703 or RS530 in terms of synchronous interfaces, also referred to as RS422 or RS485. Mimomax supports all of these interfaces at 64 kilobits. We support X21 and the RS530 synchronous interfaces at 128, 192 or 256 kilobits, and the RS232 is supported natively, so we don't require an interface for RS232, and that also supports mirrored bits natively on the platform as well, which is a teleprotection standard from a teleprotection relay vendor. So those interfaces are supported, and what we have on our radio is what we call MSync. So MSync is a synchronous protocol that provides the latencies designed for Cat 1, 2, and 3 teleprotection. And depending on the category of teleprotection you're looking at, then our radio links can be cascaded to cover greater distances. And given we're full duplex, you're essentially doubling that latency, but you're not taking a hit on capacity when you are inducing multiple hops into the design. Mimomax are also concerned or aware of the requirements in substations for EMC and EMI, especially around large disaster events which may cause an outage. It may cause significant arcing, local and electric noise, and the like. So Our radios have been hardened around EMC and EMI. They're all noise sealed around the product, as well as environmental sealed. And we have isolated ports. So the power supplies are completely isolated. They will operate either a positive or negative supply. And we also have isolation between the radio interface to prevent ground loops and ground noise problems. So consideration to the types of environments that we'll be working in and the likes has sort of been key to the design. In fact, in some cases, the diagnostics on the radio have been able to pick up fault events prior to them actually becoming an issue. So picking up noise signatures in our constellation spectrums and our diagnostic tools on the radio have often indicated that there is some form of arcing or failure about to occur. And it's been interesting to sort of identify and look at those signatures over time, and often we can see corona or other things appearing within the spectrum, which is an interesting byproduct of the type of technology we have, which is continually equalizing and monitoring the channel and working with those equalizers to maximize capacity, but also the equalizers are picking up other components that are happening in the spectrum. So the Mimomax Tornado OPVT product, which is the optimized protection variant, this is the synchronous serial latency table. So what you see here are the interfaces across the top, the bandwidth down the left-hand side, and the modulation levels that relate to all the different latencies that would be attributed to those interfaces. So these are all measured in milliseconds, and they're rated to a single hop and a one-way type of latency, not a round trip latency. So if I look at, I'm not sure if you can see where my mouse is, but on the C3794 interface across the top there, which is the fiber interface, we can look at a 50 kilohertz channel, and if we provisioned 16 QAM modulation across that link, then we would attribute 3.7 milliseconds of latency to that type of configuration. And when you pick that up, or able to support QAM 256, then that sort of reduces below that 3 millisecond number that we were talking about earlier. 550 kilohertz channels are licensable by the FCC. Some of you may already have them available. They are certainly licensable in 900. I think we've seen them in 400 as well. And for those of you that do have 700, obviously you can utilize those channels as required based on the rules around 700 meg licensing. 25 kilohertz channels, which we know are available in 400 and 900, very, very good latency there as well. Sub 6 milliseconds for 16 QAM using C3794, and that reduces a little bit at QAM 256. And then even in 12.5 kilohertz channels, you can come under that category 2 and category 3 protection requirement. Running 64 QAM, for instance, with C3794 would provide a 9 millisecond latency link. So really, really good low latency achieved through optimizing narrowband license technology and optimizing that for protection variant type radios. So if you're interested in the actual raw aggregate data rate for the MIMO product, and this is what we're showing here. So the aggregate raw data rate in a 12.5, 25 or 50 kilohertz channel is shown against the modulations, and that is either QPSK, 16 QAM, 64 QAM or 256 QAM, and the selection of those modulations are dependent on the link design and what type of availability that you'll be seeking to achieve. So that is at 64 QAM in a 50 kilohertz channel, that's 960 kilobits of data. Remembering that that is the aggregate data, so that is the full duplex aggregate, which is the sum of the uplink and the downlink. Given both of those links are independent, it means that you could be pushing a software upgrade while also monitoring the technology that you are connecting to in the field without impacting that. So pushing a software upgrade does not impact the uplink communications at all, because everything is happening concurrently rather than synchronously, which would be the case for half duplex. And on the right hand side, what we see is the sensitivities which we would be designing to meet those types of data throughput requirements, or to try and hit those modulation levels. Often our customers will ask for a recommendation, and what is typical for a customer that's looking for a C3794 interface. It is often used because it's not a conducting interface, and it is not likely to have electrical noise or other things induced on that circuit. Therefore, it's ideal for teleprotection applications. We recommend a 25 kilohertz channel. 16 QAM is typical of what we would design into those networks. And again, we've sort of talked about C3794, but we can also provide teleprotection options using X21 or the other interfaces that we've talked about as well, including legacy 4-wire audio. Mimomax teleprotection case studies. So in New Zealand, we have deployed this extensively, and in other parts of the world we have as well. So globally now we have a customer base that is using Mimomax technology in teleprotection applications, and where it has become apparent in New Zealand is in the deployment of rural areas, crossing farmlands, hills and coastal terrain, and the imagery there is a good example of what New Zealand terrain looks like. It is quite undulating, hilly. In other areas, it's quite mountainous. It is not flat or desert-like at all. It is extremely a lot of water around, a lot of coastal region, and a lot of inland lakes and rivers and the like. So that's a good example of the type of terrain and what our customers were finding. In this case, Orion was our local customer. They were struggling to get microwave linking into these sites, and the cost was becoming challenging and prohibitive, and they came to us and said, what can we do? And at that point we had the MIMO technology. We knew that it was very fast technology, low latency, so we met the latency and phase requirements, and it meant that they would not be so dependent on fiber or microwave linking in these regions. So the key aspect here was being able to provide the customer with a mission critical grade solution that was not that could be easily deployed with low cost and operate in some stringent environments. So in the winter, this would become quite snowy and icy also. So we designed and developed the optimized protection variant on the back of utility requirement. And over time, that network has continued to build, and it has got now quite a substantial network. So we're offering complete substation protection in addition to SCADA, in addition to voice over the radio link, and we've talked about the benefits of the wide antenna and the low cost of integration. Other customers that have looked and tested our devices, here's an example from Puget Sound Energy in Washington State. They set up 2 SEL line protection relays. They wanted to test the latency of the product. These relays were initially tested back-to-back, excuse me, and we then inserted Mimomax radios back-to-back within those links. They looked at the round trip latencies from the initial back-to-back test, and then looked at the latencies with the links included, and from there they derived a one-way latency, which is shown there of QAM 256, 64, or 16 QAM, all showing less than 5 milliseconds latency contribution from the communications device. So that was a really good test and endorsement of what we were saying, and that it could be achieved as well. The linking kits. So Mimomax are about to release our Teleprotection linking kits. They are antennas and radios and everything needed to make those links operate and work with the various media converters provided. So a very simple kit and bundle provided to meet the mission critical teleprotection requirements for those links, and also fully redundant linking kits as well that we are releasing. So that's all bundled and packaged and ready to go, and simplifies installment and procurement, etc. So Q&A. So did want to make sure we had time for some Q&A, and we've got sort of 9 minutes left. Thank you for hanging in there. I hope it's been informative. I'm just going to hand over to James, because James has been monitoring the radios and the Q&A questions concerning the radios. So James, I'll just hand over to you to pick up on the Q&A.
Thank you, Paul. So yeah, we've had a few questions coming in. The first question it's going to look at is, do the modulation levels have an impact on latency? So yeah, they do impact the latency. So we had the table during the presentation there. Well, from a latency point of view, it might seem attractive to pick the widest bandwidth and the highest modulation, which gives the lowest latency. From a overall system point of view, that's not necessarily the best best decision. A lower modulation, 16 QAM or even QPSK, has a much better sensitivity and is much more resilient to noise, and a narrower bandwidth also has much better sensitivity, but the highest modulation on the widest bandwidth gives the lowest latency. So most of our existing teleprotection installs are using 25 kilohertz 16 QAM, and that's providing a 64 kilobit per second teleprotection channel and having a further 64 kilobits per second of user data rate in each direction for other services. Things to consider when picking the modulation rate and the bandwidth are what's the path profile, what's the path loss there, so and that leads to what the received signal level is, and for different availability criteria, you need a different amount of fade margin above the sensitivity. So to get the most resilient link, you would pick the lower modulation and bandwidth that still meet your latency and data rate requirements. Right. Another question we've had is the Tornado FCC approved for use in the US? So the Tornado has FCC approval in the 400 megahertz band, between 440 and 470 megahertz, and the 700 megahertz upper A band, and also an 800 and 900 megahertz bands from 806 up to 960 megahertz. Another question was, do we have a management system? So We do have a management system from a third party that we have worked on adding support for our products into it, and we do provide that. So that interfaces the radios through SNMP, and the radios have been managed by our customers using other standard SNMP management tools. We've had a question on, is there a GUI interface for configuration? So for configuration of the radios, we've got both a GUI interface that runs through the web browser, so that can be connected via HTTP or HTTPS, and then we have the command line interface via SSH or a serial port. And I had a question here that I'll pass on to Paul on the budgetary cost for a UHF hop of Mimomax Teleprotection linking kit with a C3794 interface and a Yagi antenna.
Yeah, so what we have is we've actually got a Teleprotection bundle that wraps all of that in. So we have that that is about to be released, and that is downloaded, can be downloaded, I think, from our website, and we'll also be sending that out after the presentation. So within that bundle, I believe we've got some various bundles depending on the application, and we've got some fixed pricing there. So what we'd like to do is be able to have people digest that, look at what they need in terms of interface, and we can help with antennas, etc. And then what we would do is sort of bring that kit together for them as a simple link. So I think it would just need a discussion to make sure that the alignment of the requirement and technology aligns, and but that will be essentially a fixed price bundle, and we can have a discussion around that. Thanks, James.
Yeah, thank you, Paul. So I see we're getting to the end of the hour for the webinar. So we do have some more questions, and we will we'll send the responses back back to those who have asked them, and I'll leave it to Paul to wrap up.
Yeah, thanks, James. So I'd just like to thank everybody for joining. We do have those bundles. We now have the Teleprotection brochures that we'll be sending out. Here are our contacts. So in North America, on the West Coast, we have Dennis managing the West Coast. Central, we have Terry, and on the Southeast and East Coast, we have Keith. We do have these bundles available. We do also have demo equipment available, but we would be happy to have a conversation. And I think initially it starts with, is the link going to align with the technology? And sometimes that can be the first challenging step to ensure that the link is achievable, that we meet the availability requirements. So that in mind, we'd be very happy to do a link assessment, and just please feel free to reach out to the sales team, and we can arrange that, and happy to have a discussion. So just like to thank everybody for joining us here in New Zealand. It's morning time, but I understand in the US it'll be later in the day and in the afternoon for many of you. So thank you for joining. I hope you found it useful, and certainly feel free to connect with myself on LinkedIn if you wish, or with our sales team, and we can arrange next steps and perhaps determining whether there's a good fit with this technology and your requirements. So thank you very much, everybody. Have a great day.